Okay, let's go. Number 1. The Black Hole Information Paradox. You're an astrophysicist on the Event Horizon Telescope team, April 2019, staring at a monitor that has taken 2 years, 8 radio observatories spread across 4 continents, and half a petabyte of data to produce a single image. The room is silent. On the screen is a ring of orange light wrapped around a circle of absolute black, 55 million light-years away, in the galaxy M87. You are looking, for the first time in human history, at the edge of a black hole, an object so massive that light itself cannot climb back out once it crosses the boundary. Your hands are shaking slightly, and it isn't the coffee. What you're looking at is the point where physics stops agreeing with itself. Inside that black boundary is a singularity, a point where Einstein's general relativity, the theory that governs galaxies, gravity, and the shape of spacetime itself, predicts infinite density and simply stops producing answers. Run the equations far enough and they don't describe reality anymore. They just return infinity, over and over, which in physics is usually a sign that the theory has been pushed somewhere it was never built to go. And surrounding that point is something worse. In 1974, Stephen Hawking proved mathematically that black holes aren't perfectly black at all. They leak a faint radiation and, over unimaginable timescales, evaporate completely. That should be reassuring, a tidy ending. It isn't. Here's where it gets strange. Quantum mechanics holds a rule considered nearly sacred, tested and confirmed in laboratory after laboratory. Information cannot be destroyed. Whatever falls into a black hole, every detail, every particle's history, has to still exist somewhere, encoded, recoverable in principle, even if no one could ever practically retrieve it. But Hawking's own math showed that when a black hole fully evaporates, the radiation it emits is thermal, random, featureless, and carries no trace whatsoever of what fell in. The information doesn't get hidden somewhere clever. It appears to be gone, permanently, which quantum mechanics says should be impossible. 2 of the most successful, most rigorously tested theories in the history of science are giving flatly contradictory answers about what happens to reality at the edge of a black hole. One of them has to be wrong. After 50 years of some of the smartest people alive working the problem, nobody has proven which one. Physicists have proposed fixes. The holographic principle suggests the information is smeared across the event horizon's surface like a projection, encoded 2-dimensionally on the boundary itself. The firewall paradox, proposed by physicist Joseph Polchinski and his co-authors in 2012, suggested something far worse. That anything crossing the horizon wouldn't drift in peacefully the way relativity predicts. It would hit a wall of ferocious, instantly lethal energy the moment it touched the boundary. Nobody agrees which model is correct. What every serious physicist agrees on is this. Something happening at that boundary breaks one of 2 foundational laws of the universe, and which one bends is still completely unknown. At a large enough black hole, you wouldn't even feel yourself cross the horizon. No flash, no impact. Just a slow, silent stretching called spaghettification, as gravity's pull on your head grows measurably stronger than its pull on your feet, until the difference overwhelms the force holding your body together. You would fall forever, from the outside, watched by anyone still safely distant. You would end, from the inside, in less than a second. And whatever information made you would go somewhere physics currently has no confirmed answer for. If information can vanish at the edge of a black hole, the next mystery isn't about disappearing at all. It's about a single object, far smaller than that black hole, that can reach out across hundreds of miles and rewrite the shape of matter itself. Number 2. The SGR 1806-20 magnetar flare. You're a satellite operator on December 27, 2004, and every gamma-ray detector your agency has in orbit just spiked simultaneously, hard enough to briefly saturate instruments never designed to register a reading this extreme, some of them essentially blinded for a fraction of a second. The source isn't a supernova, isn't a black hole merger, isn't anything your training manual has a chapter for. It's a single object, 50,000 light-years away, on the far side of our own galaxy, called SGR 1806-20. In a fraction of a second, it released more energy than the sun produces in over 100,000 years. The burst was strong enough to measurably compress Earth's upper atmosphere, briefly, from 50,000 light-years away, a genuine physical effect on our planet from an event that far off. SGR 1806-20 is a magnetar, a rare type of neutron star with a magnetic field so extreme that ordinary physics starts to behave differently in its vicinity. Estimates put its field strength around 10 to the 15th power in Gauss, roughly a quadrillion times stronger than Earth's own magnetic field, the one that moves your compass needle. At that intensity, the field doesn't just deflect charged particles the way a normal magnet does. It reportedly distorts the actual shape of atoms within a few hundred miles of the star, stretching electron clouds into elongated, cigar-shaped orbits instead of the spherical clouds that define ordinary chemistry everywhere else in the known universe. Close enough to a magnetar, the periodic table stops behaving the way chemistry textbooks describe it because the underlying geometry of the atom itself has changed. Here's where it gets strange. The December 2004 event wasn't caused by an explosion in the traditional sense at all. It was a starquake, a sudden fracture in the neutron star's rigid crust, a shift of only a few millimeters on a surface under gravity so strong that even that tiny crack released catastrophic energy, comparable to detonating the equivalent of the sun's own output compressed into a fraction of a second, all channeled outward through a magnetic field powerful enough to warp the fundamentals of matter itself. A crack a few millimeters wide, on an object 12 miles across, briefly outshone the rest of the galaxy's entire gamma-ray output combined. Physicists studying magnetars describe them almost apologetically in interviews, because the numbers involved sound invented even when cited directly from peer-reviewed astrophysics journals. A magnetic field that would erase the data on every hard drive on Earth from a distance beyond the moon, a crust stronger than steel by a factor of billions, and still capable of cracking under its own gravity. An object that behaves, structurally, less like a conventional star, and more like matter, operating under a completely different, far more extreme version of the same physics that governs everything else in the universe. One, the rest of the cosmos almost never gets close enough to directly observe. There are roughly 30 confirmed magnetars known in our galaxy alone, out of an estimated 1 billion or more neutron stars total, meaning we've only glimpsed the most extreme edge of what this kind of object is capable of doing under conditions we can barely model. If a single crack, the width of a fingernail, can outshine an entire galaxy, the next mystery isn't a single object at all. It's the very first fraction of a second of the universe itself, when space expanded faster than light is supposed to be allowed to travel. Number 3. The de Sitter horizon. You're standing, hypothetically, at the theoretical edge of everything humanity will ever be able to observe, 46.5 billion light-years from Earth, in every direction at once. Not because light has had time to travel that far since the Big Bang, it hasn't. The universe is only about 13.8 billion years old. You're that far away because the space between here and there has been stretching this entire time, carrying galaxies farther and farther apart even as their old light continues crawling toward us at a fixed speed. Do the math properly, and the observable universe isn't 13.8 billion light-years across, the number most people assume. It's roughly 93 billion light-years across. Most people hear that number once, assume it's a typo or a mistake, and move on. It isn't either. Here's the moment that makes it possible. In 1980, physicist Alan Guth proposed that in the first fraction of a second after the Big Bang, roughly 10 to the negative 32nd seconds, space itself underwent a burst of expansion so violent that regions of the universe flew apart from each other faster than light. That sentence sounds like it breaks relativity outright, the same rule that supposedly governs everything. It technically doesn't, and the distinction is one of the strangest technicalities in all of physics. Einstein's speed limit applies to objects and information moving through space. It says nothing whatsoever about the space itself stretching. 2 points can separate faster than light, with nothing physically traveling between them at all, simply because the fabric holding them apart is expanding underneath them. It is a real, permitted loophole, confirmed indirectly through detailed measurements of the cosmic microwave background by WMAP and later Planck, and it still sounds, correctly, like the rules were bent in the very first instant reality began. Here's where it gets strange in a different way. Because of that early, faster-than-light stretching and the ongoing acceleration from dark energy layered on top of it ever since, there are galaxies out there, right now, whose light will never reach us. Not eventually, given enough time. Never, under any circumstance. The space between us and them is expanding faster than their light can close the distance, meaning those galaxies have already crossed a permanent horizon of causal contact, disconnected from us for the rest of time, even though they still exist somewhere out there. We are not simply failing to see them yet, waiting for their light to arrive. We have structurally lost the ability to ever see them at all, a hard limit built directly into the geometry of the universe itself. And beyond the 93 billion light-year boundary of what we can observe, nobody knows what's actually there. Whether the universe is finite, curving back on itself somehow, or infinite, extending forever past the point we're structurally blind to, remains genuinely unresolved, one of the largest open questions in all of physics, unanswerable with any technology currently even imaginable. Space expanded faster than light once, at the very beginning of everything, and it never fully stopped doing so. If reality can outrun its own speed limit at the largest scale imaginable, the next mystery asks what happens when an entire galaxy, our own, starts moving towards something it cannot see, cannot name, and cannot stop. Number 4. The Great Attractor. You're an astronomer in 1986, part of a team led by Donald Lyndon Bell, cataloging the motion of thousands of galaxies across the southern sky. Painstaking work, one redshift measurement at a time. Individually, none of it looks strange. Galaxies drift, rotate, orbit each other in small local groups. But when you plot the movement of thousands of them together on the same chart, a pattern emerges that shouldn't exist by pure chance. They're not moving randomly, scattering in every direction the way an unbiased sample should. They're all heading, roughly, in the same direction, at the same time, including the Milky Way, including the small galaxy you happen to live inside of, right now, moving through space at approximately 1.3 million miles per hour toward a single, specific point. You name it, because the paper needs a name, the Great Attractor. Then you try to point a telescope directly at it and discover the problem. The point sits almost exactly behind the disk of our own galaxy, in a region astronomers call the zone of avoidance, obscured by the dust, gas, and crowded starlight of the Milky Way's own body. We are being pulled, at extraordinary and measurable speed, towards something we are structurally incapable of looking directly at from where we're standing. Later mapping efforts, using infrared and X-ray surveys that can see through galactic dust, partially explain the pull. Behind the dust lies the Norma cluster, and beyond it, the Shapley supercluster, one of the most massive structures in the observable universe, quadrillions of times the mass of our Sun, exerting real, calculable gravitational pull on everything nearby, including us. That accounts for a significant share of the motion. It does not account for all of it. Here's where it gets strange. In 2008, astrophysicist Alexander Kashlinsky, using NASA satellite data drawn from thousands of distant galaxy clusters, found that even after subtracting the pull of the Great Attractor and the Shapley supercluster combined, a residual motion remained, a coordinated drift in a consistent direction that the visible universe cannot explain with known mass. Kashlinsky called it dark flow. The implication, if it holds up, is unsettling on a scale most physics doesn't even operate at. Something outside our observable universe, beyond the boundary of what light has had time to reach us from since the Big Bang, may be exerting gravitational influence on structures inside it. That is not a small claim to make in a peer-reviewed paper. The observable universe is supposed to be, functionally, the whole of what can possibly affect us. Dark flow suggests the influence doesn't stop at that boundary, that whatever lies beyond the edge of what we can ever see is still, somehow, quietly pulling on everything inside it, including us. The data is disputed. Later surveys have found smaller or inconsistent versions of the effect, and the mainstream position remains cautious about how much weight to give it. But the original measurement has never been fully explained away, and the question it raises hasn't gone anywhere. An entire observable universe, drifting, in coordination, towards something none of us will ever be able to see directly. If gravity can reach us from beyond the edge of everything we can observe, the next mystery isn't a pull at all. It's a patch of sky that has been sitting there, colder than it has any right to be, since before galaxies existed. Number 5. The Eridanus Cold Spot. You're a data analyst on NASA's WMAP mission in 2004, scrolling through the most detailed map of the universe's oldest light ever produced, the cosmic microwave background, the faint afterglow left over from 380,000 years after the Big Bang, the moment light first became free to travel unobstructed across space. The map is a wash of near-uniform temperature, tiny variations of millionths of a degree scattered evenly across the whole sky, exactly what the standard model of cosmology predicts. Except for one patch, in the direction of the constellation Eridanus, that is colder than it should be. Not by a little. Colder than any statistical model of the early universe predicts is likely to occur by chance, an outlier sitting where the math says outliers this size basically shouldn't exist. The patch is real. Confirmed by WMAP, then confirmed again with sharper instruments by the European Space Agency's Planck satellite in 2013, ruling out instrument error as the cause. It's roughly 70 microkelvin colder than the surrounding sky. Small in absolute terms, but in a map this statistically uniform, it stands out like a bruise on otherwise even skin. Astronomers call it the CMB cold spot. When they looked at what occupies that patch of sky in the foreground, they found something that seemed, at first, like an obvious answer: the Eridanus supervoid, one of the largest known voids in the observable universe, a region roughly 1.8 billion light-years across, containing far fewer galaxies than it should. Here's where it gets strange. A void that size should make the light passing through it slightly colder, through a well-understood effect where light loses a small amount of energy, crossing a region with less gravity than average. Physicists ran the numbers carefully, more than once. The Eridanus supervoid isn't big enough or empty enough to fully account for how cold the cold spot actually is. The standard model of cosmology gets partway there and stalls, leaving a gap between prediction and observation that nobody has closed. Something is missing from the explanation, and nobody currently agrees on what that something is. A minority of physicists have proposed something considerably stranger. Cosmologist Laura Mersini-Houghton has argued the cold spot could be the imprint of an early collision, gravitational entanglement between our universe and a neighboring one, evidence, if the interpretation holds, that we are not the only universe there is. This idea remains disputed, unconfirmed, and rejected by most of the field. It has not been ruled out either, which is its own kind of unsettling. What isn't disputed is the raw observation. There is a specific point in the sky, roughly 3 billion light-years wide, colder than physics fully explains, sitting inside the oldest light we can see, light that has been traveling toward us since before galaxies existed. We are looking directly at an anomaly baked into the birth of the universe itself, and the standard model runs out of explanation before the temperature drop does. If an entire region of ancient light can carry a cold spot nobody can fully account for, the next mystery isn't cold or quiet at all. It's a single explosion that outran the physics of every dying star ever properly recorded. Number 6. AT 2018. Cow. The Cow. You're an astronomer monitoring alerts from the Atlas Sky Survey in Hawaii, June 16, 2018, when a new point of light appears in a spiral galaxy roughly 200 million light-years away, and does something nothing in the survey's database has done before. Within about a day, it goes from invisible to one of the brightest transient objects in the observable sky. Supernovae, the deaths of massive stars, typically take 1 to 3 weeks to climb to peak brightness, governed by the physics of a shockwave fighting its way through the star's own outer layers. This object does it in under 48 hours. Astronomers scramble telescopes across the electromagnetic spectrum toward it within hours, before anyone even has a proper name for what they're looking at. The automated system had already assigned one, almost by accident, a T-2018 cow. Astronomers, because astronomers, start calling it the cow. Here's why the speed matters more than the name. A standard supernova is powered by an explosion pushing outward through a star's bulk, and the size of that star sets a hard floor on how fast the light can brighten. There's simply too much stellar material in the way for it to happen any faster. The cow blew past that floor entirely, reaching a peak luminosity 10 to 100 times brighter than an ordinary supernova in a fraction of the expected time. Whatever powered it wasn't shining through a star's usual mass. It was behaving like something shining almost directly from the source. Here's where it gets strange. Follow-up observations using Chandra, NuSTAR, and ground-based radio telescopes found the cow producing X-ray and radio emission far stronger and stranger than any known supernova generates. Buried inside that X-ray data, researchers found something that looked like a rhythmic flicker, a signal repeating on a timescale of minutes, the kind of pattern associated with something spinning. Multiple research teams, publishing independently, proposed the same unsettling possibility. The cow might be the birth of a black hole or a neutron star, caught in the act, in close to real time, for the first time in the history of astronomy. Not the aftermath of a stellar collapse examined years later in the wreckage, but the newborn compact object itself, still devouring the debris of its own creation, broadcasting its birth outward before anyone even knew to point an instrument at it. Other researchers weren't convinced. A competing analysis proposed the cow wasn't a dying star collapsing inward at all, but a star being torn apart by a previously undetected, mid-sized black hole, a category of object, intermediate mass black holes, that astronomers have struggled for decades to confirm exists anywhere. Both explanations remain published. Both remain actively defended. Neither has been ruled out. 6 years on, the cow remains the best-studied member of a class of objects astronomers now call fast blue optical transients, and it is still the one nobody can fully explain. Something, somewhere in that spiral galaxy, 200 million light-years away, briefly outshone nearly everything around it, did it faster than the physics of dying stars says should be possible, and then went dark again, leaving behind a scientific argument that has already run longer than the explosion itself did. If a single explosion can defy the physics of how stars are supposed to die, the next mystery doesn't involve an explosion or even distance in any way that makes sense. It involves two particles, on opposite sides of the galaxy, behaving as if the space between them was never really there at all. Number 7. The EPR paradox. You're a member of a research team in China, June 2017, watching data come down from a satellite called Micius, 300 miles overhead, purpose-built for exactly this experiment. 2 photons were split from a single source aboard that satellite and beamed to 2 separate ground stations 745 miles apart. You measure one. Instantly, the other, still hundreds of miles away with no possible signal in between, snaps into a matching state. No delay you can detect. No signal crossing the distance. No physical thing traveling between them that any instrument has ever detected in this experiment or any other. Einstein called this spooky action at a distance, and he hated it so much he spent the last decades of his career trying to prove it couldn't be real. Here's the setup, plainly. Quantum entanglement links 2 particles so that measuring the state of one instantly determines the state of the other, no matter how far apart they are. A foot or a light year makes no measurable difference to the correlation. Einstein's objection was reasonable, grounded in the physics everyone already trusted. Relativity says nothing, no signal, no information, no cause, can travel faster than light. Entanglement looked like it broke that rule outright. He proposed hidden variables, secret preset information carried by the particles from the moment they were created, to explain the correlation without anything actually traveling instantly between them. A tidy, comfortable explanation, testable, decades later, by people with better instruments than Einstein ever had, and wrong. In 1964, physicist John Bell devised a mathematical test, a specific inequality, that could distinguish hidden variables from genuine, instantaneous correlation. Starting in the 1970s and 80s, physicist Alan Aspect ran the first real experiments testing it. Anton Zeilinger and John Clauser refined the tests further over the following decades, closing every loophole skeptics could propose: distance loopholes, detection loopholes, timing loopholes, one by one. In 2022, all 3 men won the Nobel Prize in Physics for proving, beyond reasonable dispute, that hidden variables do not exist. The correlation is real, it is instantaneous, and there is no known mechanism, no medium, no messenger of any kind, connecting the 2 particles across the gap. Here's where it gets strange. Physicists are quick to clarify that no usable information travels faster than light in this process. You can't send an actual message using entanglement alone. The correlation only becomes meaningful once you compare results through an ordinary light speed channel afterward. That caveat is true, and it is also almost beside the point. Something is coordinated across 745 miles with 0 measurable delay. Two particles that shared an origin, then traveled in opposite directions for years through open space, remain connected as if the distance between them simply doesn't apply to whatever holds them together. Locality, the assumption that things can only be influenced by their immediate surroundings, the bedrock assumption underneath essentially all of classical physics, does not survive contact with a single entangled photon pair. What connects two particles across a distance light itself takes 4 milliseconds to cross, with nothing detectable passing between them, is not a fringe theory. It's proven, repeatedly, in some of the most carefully controlled experiments physics has ever run, and it's still not understood. If distance means this little to two photons, the next mystery asks what happens to something even more basic than distance, the steady, reliable tick of a second, once gravity gets involved. Number 8. PSRJ 0740+6620. You're a NASA engineer in the early 1990s, working on the newly deployed Global Positioning System, and your satellite clocks keep drifting. Not by much. A few dozen microseconds a day, an amount so small it seems irrelevant. But left uncorrected, that tiny drift would compound, hour after hour, until GPS locations were off by miles within 24 hours, useless for navigation. The fix, once your team runs the numbers, is unsettling. The satellites aren't broken. Time itself is moving at a different speed up there than it is down here, exactly as Einstein predicted in 1915, decades before anyone had a clock precise enough to prove it. That's the gentle version, the one running quietly under your phone right now, every time you check a map. GPS satellites, sitting in weaker gravity roughly 12,500 miles above Earth's surface, gain about 38 microseconds a day relative to identical clocks on the ground, and engineers correct for it in the software, every satellite, every day, or the entire system fails within hours. Time is not a constant, background thing happening at the same rate everywhere. It's a location. It depends on where you're standing. Now go further, off the scale of anything engineered. Roughly 12 miles across, weighing more than our entire sun, spinning up to hundreds of times a second, a neutron star packs the mass of a city into a sphere you could walk across in 20 minutes, with surface gravity around 2 billion times what you feel standing on Earth right now. NASA's NICER mission has been mapping the surfaces of these objects since 2017, including PSRJ 0740+6620, confirmed in 2021 to be roughly twice the mass of our Sun, crushed into that same 12-mile sphere, one of the densest objects ever directly measured. At a surface like that, general relativity predicts time doesn't just slow down slightly the way it does for a GPS satellite. It visibly crawls, compared to time measured from a safe distance. Here's where it gets strange. This isn't theoretical. It isn't disputed among physicists. It's confirmed, measured, engineered around every single day by a system sitting in your pocket. And it still describes something that shouldn't feel possible. A second, the most basic unit of experience you have, the thing you assume is identical everywhere, is not fixed. It bends around mass. It runs slower next to a neutron star than it does next to you, right now, reading this. Two people, one near enough gravity, one far from it, age at genuinely different rates over their lives, and there is no version of actual time anywhere in the universe that settles the disagreement between them. Both clocks are correct, simultaneously. Time was never one single thing happening everywhere at once. It only felt that way because nothing around us moves fast enough, or sits close enough to enough mass, to notice. If gravity alone can bend time this severely on an object we've actually measured, mapped, and named, the next mystery is smaller, quieter, and stranger. A single spacecraft, tracked continuously for decades, slowing down by an amount nobody could explain. Number 9. The Pioneer Anomaly. You're a navigation engineer at NASA's Jet Propulsion Laboratory in the early 1980s, tracking the Doppler shift of a faint radio signal crossing billions of miles of empty space. The signal is coming from Pioneer 10, launched in 1972, the first spacecraft to travel through the asteroid belt and past Jupiter, and by now it's headed out of the solar system entirely, into interstellar space. Its trajectory should be simple physics, the sun's gravity pulling it back, weakening predictably the farther out it travels, exactly the way orbital mechanics has worked for 300 years. Your calculations don't match the signal. Something is slowing the spacecraft down more than gravity alone accounts for. A tiny, consistent, unexplained deceleration. And it isn't going away no matter how many times your team reruns the numbers. The number itself is small, approximately 8.74 times 10 to the negative 10th meters per second squared. A figure so minuscule, it took years of clean tracking data even to confirm it was real and not simply noise in the instruments. But it was consistent, present in Pioneer 10, present in its twin, Pioneer 11, launched a year later on a completely different trajectory heading toward a different part of the sky. Two independent spacecraft, launched separately, tracked separately, both drifting slightly off their predicted paths, both slowing by the same tiny, persistent amount for decades on end. Here's where it gets strange. For over 20 years, nobody could explain it. Every conventional cause got proposed and tested and ruled out, one after another. Solar wind pressure, too weak, by orders of magnitude. Drag from interplanetary dust, negligible at that distance from the sun. Onboard fuel leaks, considered carefully and largely dismissed. The anomaly held steady, no matter what mundane explanation researchers threw at it, and the possibilities being seriously discussed got progressively less mundane as the years went by. Modified theories of gravity were proposed in respected journals. The possibility of unaccounted dark matter in the outer solar system was raised in serious peer-reviewed papers by serious physicists. For 2 decades, one of the most reliable, well-tracked pieces of engineering humanity had ever built was quietly defying the very physics used to design and launch it. In 2012, a team led by Slava Turishev, publishing in physical review letters, finally traced the cause: heat. The spacecraft's own radioactive power source was radiating thermal energy unevenly, off-axis, creating a tiny but entirely real recoil force, like an extremely faint, extremely slow rocket thruster made of waste heat instead of fuel. Mystery solved, mechanism confirmed and published, case closed, more than 20 years after it first opened. Sit with what that timeline actually means. It took a dedicated research program spanning 2 decades, drawing serious attention from professional physicists willing to entertain genuinely new physics as a real possibility, to eventually rule out something that turned out to be entirely mundane. One known spacecraft, extensively documented, continuously tracked by multiple agencies, still took 20 years to fully explain. It raises an uncomfortable question about everything else out there that we aren't tracking nearly that closely, that isn't broadcasting a clean signal home for anyone to notice, a multi-decade anomaly slowly resolve. If a single, fully monitored spacecraft could defy explanation for 2 decades, the last mystery on this list is bigger than any single object. It's the discovery that whatever is pushing the entire universe apart, faster every year, doesn't match its own theoretical prediction by a margin. Most people will never see written out in one place. Number 10. The vacuum catastrophe. You're an astronomer with the High Z supernova search team in 1998, measuring the light from distant exploding stars, Type 1a supernovae, the kind that always detonate at the same known brightness, making them reliable cosmic yardsticks for measuring distance across billions of light years. You expect their light to confirm what everyone in the field assumes, that the expansion of the universe, set in motion by the Big Bang, has been gradually slowing down ever since, dragged backward by the combined gravity of everything inside it. Your data says the opposite. The distant supernovae are dimmer than they should be, which means they're farther away than expected, which means the expansion isn't slowing down at all, it's speeding up. A second, entirely independent team, the Supernova Cosmology Project, working with different data and different methods, finds the exact same result. Gravity should be the universe's brakes, the one force everyone agreed was pulling everything back together. Instead, something is stepping on the accelerator, and it's been doing so for roughly the last 5 billion years, more than a third of the universe's entire history. In 2011, the discovery earns Saul Perlmutter, Brian Schmidt, and Adam Riess the Nobel Prize in Physics. The cause gets a placeholder name because nobody can define what it actually is, only measure what it does: dark energy. Here's the part that should not be treated as ordinary background trivia. Current measurements attribute roughly 68% of the entire energy content of the universe to dark energy. Not a minor correction term buried in a footnote. the dominant component of all existence, outweighing ordinary matter, outweighing dark matter, driving the large-scale fate of everything that exists, and there is no confirmed physical mechanism behind it whatsoever. It has never been directly detected in any experiment. It cannot be isolated or produced in a lab. It is inferred entirely from its effect on the space between galaxies, and its effect is that space itself is stretching faster every single year that passes. It gets stranger. When physicists try to calculate dark energy's expected value from quantum field theory, treating it as the energy inherent to empty space itself, vacuum energy, the predicted number and the observed number differ by a factor of roughly 10 to the power of 120, a 1 followed by 120 zeros of pure disagreement between theory and measurement. Physicists have taken to calling the gap the vacuum catastrophe, and physicist Michael Turner has referred to it as the worst theoretical prediction in the history of physics. That is not hyperbole added for a script. That is a description used inside actual peer-reviewed cosmology journals. The implication, if current models hold up, is not comforting. An accelerating expansion pushes galaxies apart faster and faster, forever, with no known mechanism to slow it back down. Eventually, distant galaxies cross a threshold where their light can no longer reach us at all, redshifted into permanent invisibility. The night sky, over trillions of years, quietly empties out, not because the universe ends, but because the force expanding it never stops, and nobody currently knows what that force actually is. 68% of everything that exists is being driven by a mechanism physics cannot name, only measure from a distance, off by more orders of magnitude from its own best prediction than any other number in the history of the field. 10 places, 10 forces, 10 objects breaking the rules that are supposed to hold reality together, and one pattern underneath every single one of them. Modern physics can describe an enormous amount of the universe with extraordinary, checkable precision, and it still runs out of answers at the edges, again and again, in ways specific enough to have real names, real dates, and real data attached to them. From a black hole quietly erasing information to an entire universe expanding for reasons nobody can name, the dark keeps leaving evidence of rules it isn't following. If any single one of these 10 unsettled you even a little, subscribe for more of what's actually out there waiting in the dark. Drop a comment with which of these 10 broke your brain the hardest, and let us know exactly where in the world you're watching this from.